Cool. Thank you, everyone. Right, thank you. Right, well, hello, everyone. I'm Ed. I recognise a few of you, and some people I've just met today, which is good. I'm going to talk about a project I did when I was a member of CE Spaceflight, which was the case until I graduated last year. And specifically a project that we took part in for the European Space Agency to test some parachutes. I was going to give a quick introduction to Cambridge University Spaceflight for people who didn't know, but I think the last minute on that, so that's fine. That saves me some effort. So in the summer of 2008, I was working for my holiday job for a company called Vorticity in Oxfordshire, who were doing work on the ExoMars landing system. And ExoMars is a European rover due to, well, it's now been split into two separate projects, one in 2016 and one in 2018. But at the time, it was a rover that we were going to land on the surface of Mars. And to do that, you need parachutes. And I was working whilst I was there on some tests for the parachutes in a wind tunnel. Now, the full-size parachutes for the rover were about 20 metres in diameter, which is enormous. And we had manufactured some subscale ones about 2 metres in diameter, which we tested in this wind tunnel. This wind tunnel is one of the biggest that you can afford if you're not NASA in the world. It's in Canada. It's a 9 metre by 9 metre working section, and the parachutes are attached to a pillar there, and they get deployed into a stream of fast-flowing air. Now, the only problem with this is that on Mars, the atmosphere is about 1% as thick as Earth's, and the parachutes will be deployed at a much higher speed. And this is because what you're really doing with parachutes is the way they open, and the way they open is affected by things like your Mach number, your mass ratio, which is a ratio between the mass of your system that the parachute is decelerating and the volume of air that the parachute sort of holds. And it affects the force profile as the parachute opens, and a bunch of other things. And you really care about it because parachutes generate their peak force during inflation, which is actually higher than their equilibrium force. So even if a parachute at a certain speed and you work out what the equilibrium drag force will be, the actual peak force will be higher. Stress, all the things that hold it. And it affects a bunch of other things as well, the high Mach number and thinner air. It affects, for example, if the parachute gets into a steady glide, or if the parachute screw, things like that. And people know about this, right? So I was also involved in planning go to the nearest place on Earth that's like Mars, and that is the top of the Earth's atmosphere. And they do that by getting an enormous balloon, building a large test vehicle which has about the same. It represents the full-size lander and has full-size parachutes on board. And they take it up to the top of the atmosphere, let go, drop it back down, it accelerates, and once they get to the right kind of conditions, which are Mach 0.8, at the right kind of overall opening forces and dynamic pressures, they deploy it. Now, about the same time I was working on this, I also had a day off work to work on Nova 8 HAPS-D, which is the flight that we did with Doug Ellison, and that was the one that took that. I don't know if you've seen it, the sort of 360-degree panorama of the Sun over the Earth, which is on the UKHAS wiki page at the moment. So eventually the conversation turned to the fact that we might be able to do this style of test with the little 2 metre diameter parachutes from here by building our own mini version of a drop vehicle. And that's what we did. And it was coined Subscale High Altitude Drop Test. So that was 2008, I thought. And then coming to the university year in 2009, I got a call from John Underwood, a colleague at Vorticity, who said, oh, by the way, ESA have now agreed to pay for that and do it, so you're doing it. And so Shadowt was born, and this is what it looks like. So we have a test parachute here, and then we have the main upper body of a vehicle. It's a sort of pointy vehicle because it has to fall quite quickly. And then a nose cone. We have the test parachute and pilot parachute, which is a kind of parachute with a big spring in it that you can press that skydivers often use as their mains. So as soon as the skydivers release the patch, they spring out and get into the airflow.
That drogue thing?
Yeah. Yeah, it's a drogue. And then because of the test, sort of pushing the limits of what it could take. We also had a very strong reserve parachute underneath in the front half, which we could deploy in case the main one failed for whatever reason. And that was also deployed by a backup spring pilot parachute. And then a nose cone. And we had a tether between the rear end of the vehicle and the front end of the vehicle. The front could actually detach from the back here to deploy the reserve. And we could optionally detach the tether so these two parts could come down separately, and you'll see why we did that later. Here's a cross-section. So again, we've got the spring pilot here, the main test parachute. Underneath we have a high-speed camera, which is going to look up at as the parachute gets deployed. It can see the parachute being pulled away and deployed, which gives useful engineering data, though it's mainly for pretty pictures. Because the really useful data comes from the electronics, which sat just behind the camera. And we had accelerometers, gyroscopes, pressure data. We could measure all the accelerations and forces and stability of the parachute as it opened.
So the whole measure those stability through the payload itself.
Yeah.
The truck.
Yeah, you can figure out the physics of what's going on, but based on the tensions from the bridle legs. And the whole thing was built around a large, you can't really see this in this picture, but a big, thick aluminium bulkhead, which was machined and everything was attached to that really. And then we had the outer tube was made of fiberglass reinforced plastic, fiberglass reinforced cardboard, and then the fins were carbon fiber. We had one flight computer in the main avionics bay here, with its own set of batteries. We had another reserve flight computer in the front with its own set of batteries. They could talk via disconnectable links, and both the flight computers could control redundant critical pyrotechnics, so that either flight computer could save us if we got into trouble. And so the flight profile looks something like this. You attach the vehicle underneath a normal balloon with a pre-deployed parachute. You ascend like a normal HAB up to about 27 kilometers. And then at that point, we on the ground uplink a command to the vehicle saying, "How you doing?" And it will say, "Yeah, I'm good." And then we say, "Okay, now begin the test." And what happens at that point is the main flight computer talks to the backup flight computer and says, "Right, I'm about to begin a test. Are you happy?" And the backup flight computer says, "Yes, we can communicate fine." And then the main flight computer says, "Okay, if you don't hear from me again in 25 seconds, something's gone wrong. Deploy the reserves." And the backup flight computer says, "Okay." And then after that, this pyro gets released, and we start to freefall. Now we've all predetermined calculation of the time we need to freefall to get up to Mach 0.8. 0.8. The rear cap is released. The spring pilot deployed pulls out the. Sorry, I've got a wobbly laser pointer. It pulls out the main test parachute. Then it's deployed, and the whole system comes down onto that main test parachute for a while until we get to nearer the ground. We release the front half with the reserve parachute and the rear half with the test parachute, so you get two much smaller, lighter landing. It's wrong. In the nominal case, we start the test, it drops, we say deploy, nothing comes out, either the main flight computer's dead or the parachute deployed but then burst straight away or something. Within about 2 seconds, either the main flight computer will have realised this because it checks accelerations and pressures and it deploys the emergency parachute, or if the main flight computer's gone down, then the reserve flight computer will have not heard back from the main flight computer to deploy the emergency parachute. We also have another pyro above the pre-deployed parachute. So if we had very tightly controlled light, if it were to fly outside, we say, okay, this test's not happening, we'll just bring the whole thing down safely on a pre-deployed parachute. And likewise, if for whatever reason the balloon burst early, we could cut away from it to get a cleaner descent. So, station, we had this rather nice accelerometer, which is a 3-axis one. We had to use a piezo accelerometer because MEMS accelerometers couldn't quite give us the range and the bandwidth we needed. Because this parachute would deploy in a few tens of milliseconds, it wasn't a particularly long window that we had to capture data that we were interested in. So we had to upgrade to this gyroscope, which had much higher bandwidth and much higher range, which we would just sample the hell out of whilst the parachute was actually deploying.
Expensive.
Yeah.
reassuringly.
Yeah. We didn't want to lose the payload. And then we had the high-speed camera. This was a real enabler. So normal high-speed cameras are sort of, I don't know, £20,000 of the kind of spec we wanted. And often they need PCI cards because they just dump the data straight out and they need to go into a RAID array or something. We obviously could fly a whole computer on there. And they were too expensive anyway. In fact, the flight computer's worth more than the project. Sorry, the high-speed camera was worth more than the entire value of the project. So we actually found, serendipitously, Casio about the same time this, which is a consumer-grade high-speed camera, which actually had really impressive performance. It could do 300 frames a second at sort of sub-VGA, but sort of close enough to VGA quality, which was just about good enough for what we wanted. And then, unfortunately, there was nothing like CHDK, so we had to solder wires directly into the back to mimic all the button pressings. But it worked, it was really good, and that was actually about £500, which was brilliant. So we had a few things. We had about 2.5 months to do this, which was quite tight. We had to develop an uplink, which we hadn't done before. I'm not sure if anyone else had done before, so that was tricky too. So the first thing we did was our cub, kind of a test to do some downlinks. And it's also a very tiny flight computer. It's a bit like Mark's mini nut that he was showing us this morning. So it's based around, I've actually got the wrong side of the PCB to be useful here. On the other side, about here, there's one of those little TI 10 milliwatt transceiver chips. GPS comes here, goes to the transceiver, has an 8051 microcontroller core and a serial port. So if you talk to the GPS, and then it can just spit the radio out. And then on I/O, and we had continuity testing on all the I/O, which is really useful for checking the pyros are all healthy, especially before you say, okay, run the test. We tested that, just how far I got an uplink, so I grew through the apartment and all the way out to the North Sea. I seem to remember Rob was listening to that one from Yorkshire as well, so the signal was pretty good.
Very good.
So that was a good flight. Next thing we had to make was the Badger. This was going to be the Badger Cub Reserve flight. This was my first ever 4-layer PCB. I recommend practicing on PCBs before you do in flight, because it's difficult.
It worked first time, didn't it?
Well, it worked with some modifications first time.
Could have extra wires on this.
Well, I finished it at about 3 in the morning, and then was too tired to do a design rule check and sent it off to the manufacturer. And there are a couple of problems internal, just a few bodges. So what have we got? We've got a ARM7 microcontroller, LPC 2368. We have a chip. The entire stick is completely lifted from the Badger Cup in that part. We have a high G accelerometer. I forgot to say the really nice accelerometer we had is AC coupled. So we needed some DC accelerometers to reconstruct what actually happened from the AC part of the accelerometer. SD card, we actually used the full SD interface rather than the SPI interface because we were having to bash data really quite fast. We were sampling lots of sensors at about 10 kilohertz resolution. It actually caused us lots of problems because, you know, if you've ever played with SD cards, they occasionally go into wait state where they say, I can't take any more data. And you get sometimes 200 millisecond lockups. And if that occurred during the parachute inflation, that would have been really bad. We have a couple of gyroscopes, a few other random sensors, pressure and magnetometer, Venus GPS. In the end, we got rid of it and put U-blocks on because they're rubbish. And then our own radio front end for a radio GPS. So this chip spits out the raw baseband IQ signals from GPS satellites, and then we were going to implement a software GPS, not for this project, for subsequent projects, because on the back of this you can fit a computer. There's actually the footprints for it, which is the flight computer James mentioned earlier on, and that had enough oomph to do the software GPS, but we didn't need it for this project, so we didn't do it.
Have you ever implemented the sideband? Have you ever
Henry, he's doing it in the States at the moment.
Oh yeah, he said he got it.
It was, I mean, there were basically we tried to launch this.
Yeah.
So it's fine for this project, but
Yeah.
we'll do it. But yeah, so it was fairly round. So the moral of this was working at some point or other to try and persuade people that we could do it, to persuade the various authorities, and there were lots of authorities and lots of insurers and lots of effort to persuade them that we could do this. So the first test was to check that our method of deploying the parachute was going to be okay. The way it worked is we had, this is the back end of the vehicle without the fins. We had an aluminium collar which had a chamfer which accepted the lid. The lid could pivot around a little lug on this side. And then over here we used pyrotechnic protractors, which are entirely self-contained pushers, and they're basically like an M8 bolt, and a pin shoots out at the end when you have a current from the wire side. And I mean, on these ones, they were M8s, they have a force of 1 billion newtons per brilliant, and also they are, because they're completely self-contained and don't emit any gas, you can just post them and buy them, and there's no problem. And they're about £35 each. They're quite a lot more hobby, but if something built, you get a nice legal way for this. The idea is there would be a grub stick, and it's in the position here. It would be flush with here, and then it would punch out, which would push the lid off. And then the spring pilot would be sitting underneath, shoot out, now the lid was free. So we tested that, and you'll see it should burst off any second now. And the spring pilot shoots out, and that would get into the airflow, and the main parachute would be attached to underneath here, and it would get yanked out.
It's just solid.
Pardon? The lid, most of the force in the lid is from the pretty give a kick. Clears, but then the spring is pretty.
Spring pushes the parachute out.
Yeah, it's within the parachute itself, the spring. That's the pilot. We'll do it once so you can see. So there's a spring within the parachute. Boing. You can kind of see it.
Oh yeah.
Oh, this is for the camera.
Look at you, sir.
Yeah. So then the next test is well, let's check assemble this back beneath and okay. So we tried to look for a wind tunnel. It turns out the only kind of wind tunnels you can use are things one I showed you in the first slide, which are way out of our budget, because the percentage of blockage of physical objects in a wind tunnel before the results become invalid. So in the end we made a gangster wind tunnel by the back end to get onto the rear plate, attaching that to a steel plate, attaching that to the back we bodged onto a trailer, attaching that to the back of a Dodge Ram, and go to airfield and trying out. And then we got the onboard video as well. There was a bit of a crosswind across the runway that day, so the parachute's slightly over to one side. But in the real thing, it was in the middle because there weren't any crosswinds. So, next test, once that was proven, was to basically take that we flew on the back of the trailer and take it up under a balloon and see if we could do a static deployment. So not a free fall, but just a from standing deployment of the parachute. So that was to check the uplink on Badger 2, take the temperature, all the other things like that. So this looked pretty at one point, and then it started raining. So we put some last minute waterproofing on, padding and what's in here. But the important bit is that there's a pyrotechnic here, and that's holding the very top of the parachute down. Sorry, the very top of the bag down. The test parachute deployment bag is attached to any normal flight. This slots up. And then we uplinked a command that would say blow this link, which means that this part of the vehicle from beneath the red line would fall away from the parachute sleeve and deploy. And here's that video. No, this isn't helicopter yet. I agree. Yeah, so the parachute. Sorry, there's the. We yank out of the parachute bag. There's no dynamic pressure because we went from 0 miles an hour, so it starts to tumble a bit. This was about 28 kilometers. You can see the parachute here, just doing its thing. Later we get it correct. Any sound? So this is all the high-speed camera. Faster. And there you can see the parachute's inflated, and there's the balloon we deployed away from with the pre-deployed parachute and deployment sleeve underneath it that we put out. So that all worked nicely. A quick note on real-time prediction and its value. Whilst this happened, we uplinked the command. So we were in the chase car, we uplinked the command saying, okay, our prediction says it's going to land somewhere, so start now. And the flight commander said, okay, bursting in 5, 4, 3, 2, 1, go. We ran a go and drove to exactly where it told us to go. And this was the result. So this blue line is the prediction that was run, is zoomed in at the end of the prediction that was run on burst. This is where it reckons it will land, this is where it actually landed, and that was from 28 kilometers. So we were quite pleased with that. And in fact, just to show off a bit, we went here, we were parked here, and it was a really overcast, rainy day. As I say, it was raining in Cambridge last minute. And so we couldn't really see it coming down or anything, but because the cloud level was so low. But when the flight computer said, okay, look up now, and there it was. So you can see there's the main test parachute, and there's the vehicle, and it was a couple hundred metres away going overhead. So that was all good.
Was that water that I saw next to it? Was that big pool of water?
Yeah, we don't talk about that. Yeah, so that was close.
Is that where you said it was a really good time to launch at that point?
Yeah. We thought more of large numbers.
Yeah.
With your prediction, was it in fact that you were actually modelling parachute dynamics so that you knew you were the set range?
We had good information about our parachute, but the dynamic prediction should be able to model. All you need to know is the ballistic coefficient. Right?
Yeah, okay, fair
You're
investigating that anyway, really, so yeah.
So once you get a good figure of ballistic coefficient, and I think we had fairly fresh grips on this.
Yeah, once it starts to drop, you should know.
Yeah.
You know, do a few measurements on.
Within the first few meters, it should be. Well, the first few minutes, it should be. Yeah.
Was that pirate these tube ones?
Yes, that was.
One of the homemade.
Yes. Yeah, sorry about that. Well, for everything official, we use the pyrotechnics, but yeah, that was one of my homemade ones. But your design, anyway.
Just interesting.
So, the final test we wanted to do was, let's see if we can do the whole thing together, end-to-end test. So that would be deploy the main out the back, split halves, land as 2 spots. Obviously we wanted to actually test it somewhere safe before doing it for real. So we wanted to compress all this, and we reckoned we could do it in about 150 meters if we did it at sea level. So just fall for a few seconds, deploy, reach equilibrium, split into 2, land. And because we knew about balloons, we thought balloons were the best way to do this. This was completely wrong. The first time we tried it, what happened the first time we tried it? Oh yeah, we didn't quite, well, the first time we tried it, we had the vehicle in a field, and I tried to drive home to pick up, or drive back to the lab to pick up something, and then some cows broke in and started chasing our friend Dan. So I saw Dan in my rearview mirror holding the vehicle, just charging, whilst 100 cows suddenly appeared again behind him. So I had to turn the pickup truck into a sheepdog and was kind of driving around hooting at the cows, trying to have back in. So that was bad. The second day, I thought, second time lucky, We'd inflated that. We really wanted to get quite a lot of helium in this balloon because we really wanted it to be lifted high and really lift this whole system up. Because I got 250 meters of tether line, I wanted 150 meters, so I thought it needs to be above about 60 degrees. And I was sitting there holding it was being filled. And then, as we were just finishing up, there was this bizarre noise. It was a bit like a kind of thump. And then I was sort of looking around to see what the cause of this noise was. The fill rig. And the other bit of fill rig is attached to the balloon, shooting up at about 15 meters per second. So that was a bad day. And then...
That was 3,000 grams, wasn't it?
Yeah, they all were.
Excellent business.
Yeah, exactly.
Don't do that as much as you
Yeah.
Very pissed off at that though.
Well, that was actually that was about the time that you were doing that stuff with the sun, when I came and sort of grunted at you a bit at Churchill. And and then third time lucky, we set up in the field again. There's the vehicle, there's the sheepdog pickup truck, helium and balloon. We inflated the balloon, as I say, we really inflated the balloon. So there's me, and there's all the balloon. We had about 18 kilos of lift on it in the end. Things seemed to be going all right. The whole thing was being lifted up quite nicely. As I say, because we've had 18 kilos of lift in there, there's a great deal of free lift in there, although it had 250 meters times 3, so we had 3 250 meter lines to it, because we didn't want it going anywhere, because that would be bad. But actually, balloons are just not a stable shape aerodynamically. They shed vortices off, and they bounce around a bit, and they start swinging quite a lot. I'm not sure if you can see this, but there's Fergus and there's me. And we're trying to let the lines out, and there was only about 6 mile an hour winds that day, but it was trying to cut through our gloves, the wires on this, and we had each a tether wire with a 30 kilogram lump mass, and it was just pulling them across the field as if they weren't there. It was pretty scary. So we shackled them onto the fence. And then that was about as high as it got, it was 60 meters. But it kept basically bouncing, the whole thing was sort of up and down. And that was spent most of its time. So the balloon is about 150 meters away from the person taking the photograph. I mean, a really shallow angle on the tether lines. And eventually what happened was it got up to about 180 meters and seemed to stabilise a bit. We thought, oh, bring a message from the radio transceiver saying, oh, by the way, I'm not talking to the flight computer anymore. So as it started bouncing up and down again, Fergus and I started charging underneath trying to find this thing. Someone described it as like lions trying to catch a gazelle, which I think was probably overstating it slightly. And yeah, so we eventually grabbed this thing out of, as it was sort of bouncing up and down, reset it, and thought, okay, it's now or never. We let it go up again, and it went up really high. Then there was a gust, and it came smashing down to the ground and took the fin off. Which we tried. This is a bit of an in-joke. We were working. We basically had some Italian colleagues, and every time something went really wrong, they'd say, "Oh, he's okay," like that. It became a bit of a meme for us that summer. Like the flight computer was a massive mush cloud of magic smoke would come out of the flight computer, and everyone would stop and stare. And like, he's okay. Anyway, yeah, so we were sort of a bit fed up by that point. Anyway, so we thought, well, this whole tether balloon thing is really, although Steve made a nice profit that week, it's really not the way to do it.
Don't make a profit.
No. It's just not the way to. They're just not stable, basically. So we decided, we actually ended up doing what we should have done in the first place, which was about 10 times cheaper, 10 times less effort. Although it seems a bit extreme, it's really a lot easier, and that's this. guys. So basically, that was a really nice day after all the effort. Because although I've shown you some of the prettier tests, there was the whole time we just test, and lots of things didn't work lots of times, and it was getting a bit depressing. So we were.
How much it cost to hire the helicopter for the day?
Pardon?
How much it cost to hire the helicopter?
We didn't hire it for the day. So the helicopter is 400 quid for a pilot for a day, and then £1,000 per flight hour. And we only needed 1 hour, minimum 1 hour. So it's £1,500. The 3 failed balloon attempts, all the balloons were about 300 quid each. The helium's about 100 quid a bottle, and there were 9 bottles. So yeah. So, and helicopters can just well, we didn't factor in time. I mean, Jesus, that would be depressing. But anyway, we've got a working system, plus with a few other tests. You can hear the camera snapping away. These are the photos it was taking. So we start off with the vehicle hanging beneath the helicopter. You'll notice a big gym weight there. That's because if this detaches and this tether recoils, then the helicopter pilot can get a bit annoyed. Then it goes into free fall. This is a nice photo. So there's a spring pilot chute, which has pulled the entire flight train taut. The parachute deployment sleeve is taut, and you can see the parachute just about to pull out there. Here it's fully deployed.
Do you have runners on the line?
Runners?
Yeah, that slow the deployment down.
I know exactly what this...
Reefing?
Reefing, thank you. Sorry, I should know that's my job. No, we didn't have reefing, because reefing is actually quite unreliable and defactorised, and it tested. It wasn't going to be on Mars, so they weren't going to do it on here. They're very conservative, all the space agencies. They pretty much all just do what worked for Viking, because they're expensive test Viking, firing rays in sort of Mars. Everything, Spirit and Opportunity rovers, the Curiosity rover, all in type data. So if you were to suggest reefing, they probably all break out in sweat. Anyway, and then so once it's reached equilibrium, it deploys the front half, and there's the front. Does anyone know Aerocon Systems, the aerospace toys? Anyway, that's one of theirs.
Cheap?
Yeah, about 30 quid. Yeah, really cheap. And then it landed. So, people were saying this is worked. So the big day came. See the reflection of the camera lens there, a few hundred meters away, the front half, and what happened in between that and this is everything had worked, and we were a bit dumbfounded. I mean, it sort of worked. We said, okay, start the test, and we said, start the test, and he went, you what? And so we cranked the power right up the direction. Start the test. Okay. So it's fine. I guess I should show you the video from on board. I'll show it to you again.
That's slow motion.
Yeah. It's the same speed as the other one I showed you. So I'll show you the slowed down version. You can see something really bad happens. It starts off okay. You get lines taut and the thing goes out of focus. And then it stays kind of out of focus, and as the parachute in place, it starts zooming in. And what had happened, which we realised almost straight away, but one of the few things we couldn't test for, is the linear actuator which controlled the zoom in the high-speed camera just went, oh, you're joking, when it saw 100 Gs. And so the lens just went down into the sensor as the parachute inflated. That was really sad. But all the actual engineering data was good. The gyros were fine, the accelerometers were fine, the SD card didn't blank. Well, we got around the whole issue of the SD card blanking out. But basically, that was it. That's the story. So we have a whole paper which we published and presented at a conference in Dublin a few months, has all the results and the physics and the graphs and all the parachute bump. This is really just what we did, how it worked for us, show and tell. So if you want to read the paper, there's a link to it on our website, or I can post it to someone. But really, that's it. So thank you very much.
Thank you. Let's see the lens to go.
No, it's fine. Yeah, we used the project, so I've since taken them apart to actually lock the carriages inside, which was a bit hairy, but it's basically, it's sort of a tight friction, but not very tight fit on the linear actuator, so it just slipped off. I can fix it. If anyone wants the cameras for things, I've got a pictorial on how to take them apart and modify them to press all the camera buttons and lock the lens and the manual focus and stuff.
There is a question on IRC actually where someone's asking, can you give details of the actual make and model, which I know was on the things,
It's
but obviously they can't see it.
Casio EX-F1. They're still floating around on eBay, but they're not sold anymore.
Did you detach the drogue from the main chute deliberately?
Yes, because we just wanted the aerodynamics of the main chute.
Is it just a breakable link?
No, it was so it was packed inside the deployment sleeve. There, so you can see that it's an outer Kevlar sleeve which is a bit yellow, and then there's a green parachute underneath which sits in it, and it's just there's a tiny little 5 Newton link attaching the apex of the parachute to the inside of the sleeve when you pack it, but that breaks straight away, so the sleeve gets left behind. And it's nice. I mean, if you're doing rockets and stuff as well, anything deployable, it's nice to get your entire train. I mean, parachutes are basically, the opening is a kind of boundedly random event. It can be quite scary, and it's nice to control as much as possible by trying to get everything nice and taut. And therefore, when the parachute opens, it's already applying deceleration to the vehicle. Whereas if you deploy if the parachute inflates before the lines are taut, all of a sudden you can have this enormous velocity difference between your parachute and your rocket, and then stuff breaks. So it's good to get everything taut first, and then you're in better shape.
And the large fins presumably are because you're operating in altitude.
Yes, we needed the stability. We need quite a lot of stability. There's loads of stuff in the paper on FEA analysis and wobble analysis and CFD if you want. But yeah, it is just for that reason.
Did you manufacture the base, the payload?
Yeah, the whole vehicle was us. Yeah, so I mean, we bought from Malcolm Jennings, from a rocketry shop, the base tubes, and the nose cone was an off-the-shelf fiberglass one that we put everything together and glued everything on. In fact, you can see in here, I'm not sure if you can just see, but there's a new and as yet unpainted fillet of carbon fibre fillet on that fin, which is the one that broke the time before. Yeah.
Will you do it again?
For about 8 times the money, yeah. I mean, it was fun and it's a good opportunity, but in terms of making money, we didn't. I mean, we weren't really in it to make money, but it ended up being about. Well, we averaged 18-hour days, 7 days a week for 3 months. So by the end of it, we were just shot to pieces. Basically, we just had no lives left. All because we tried to fit it into a summer holiday, which was a bad idea, but it was a sort of artificial constraint imposed by holiday. So I'm glad I did it, but probably not again.
Has it been career enhancing if you hadn't have done it?
It's been useful, yeah. Well, I'd like to say we haven't seen all the. But yeah, I mean, so I'm now working for, I suppose I should say, I'm now working for Vortisti, who I worked for before, and I'm working on the full-scale version of what we did. So this. So we're going up to Kiruna in northern Sweden in the next couple of years. 700 kilogram load vehicle balloon as a full scale. So that should be good fun. I shall blog about it.
More than 90 pounds of helium, presumably.
Bit more than 9 pounds.
What sort of regulatory hoops do you have to jump through?
Quite a few, and especially working for the European Space Agency, because they're very, very tight on everything. So we had to talk a lot to the CAA, we had to get lots of written stuff from the local air towers. Insurance was a really interesting one. We ended up going with a kind of experimental aviation insurance specialist in Texas who Armadillo Space, among other people, which is how I found out about them. But there was a lot of toing and froing, quite rightly, to make sure people were happy. But I think we've said again, if we do it again, we do it over a range, because the problem is there was a lot of complexity added by all this redundancy and safety stuff, and it would be a lot nicer if we could just have one flight computer, one parachute, one camera, and do it over a range, do 10 of them.
Over the segregated range over.
Yeah, sorry, yeah. So over somewhere like this in the north of Sweden, where you can actually drop tons without people getting upset.
Would it have been cheaper to do that as well in the long run? The cost of
Probably
going
not.
away?
I think I'm being recorded on the internet, so
You can turn it off for a short period if you wish.
probably not. These are very expensive, these ranges, and we were quite keen to keep it as self-contained as possible to try and make sure it happened. Full stop.
Stop there. Yeah.
Cool. Thank you.
Thank you.